We live inside a dynamic, invisible sponge. At any given second, the air around us is actively absorbing heat and holding on to floating water vapor. When engineers design climate control systems for massive enclosed environments, like 50-story skyscrapers or sprawling hospital wings, they have to manipulate that invisible volume. They cannot simply guess how much machinery and electrical energy is required to do it. They have to account for a chaotic set of interacting variables: the standard dry bulb temperature, the wet bulb temperature, the exact ratio of moisture in the air, and the total heat energy, known as enthalpy. Because these properties are inextricably linked, meaning changing the temperature instantly shifts how much water the air can hold, calculating their thermodynamic interactions requires navigating a maze of interdependent equations. To manage that math, engineers use this graph. This is the psychrometric chart. At first glance, it looks like a dense, unreadable web of intersecting geometry. But once you strip away the density, you are left with a literal map that identifies the physical properties of the air breathing around you. If we wipe away the visual noise, this chart is actually built on a very simple foundation. The horizontal x-axis maps the dry bulb temperature. This is the reading you see on a standard wall thermometer. The vertical y-axis maps the specific humidity. This represents the actual physical weight of water vapor contained within every kilogram of dry air. Then we draw the absolute limit of the map, the curved saturation line. This boundary represents 100% relative humidity. It is the threshold where the air carries the maximum amount of moisture it can physically hold, before that water starts condensing into physical drops. This simple grid defines the physical boundaries of human comfort and every indoor climate we create. If an engineer measures just two variables, say a room sitting at 30 degrees Celsius with 40% relative humidity, they can drop a pin on this map. By tracing a flat horizontal line left from this point until it hits the saturation curve, they immediately find the room's dew point, the temperature where condensation will start forming on the windows. By tracing parallel and diagonal lines outward from that exact same pin, they find the air's specific volume and its specific enthalpy, which is its total thermodynamic energy. Plotting this single coordinate makes every other thermodynamic property of the room visible at once. When you turn on an air conditioner, you are actively changing the state of the air. On the chart, you are picking up your pin and moving it to a new target destination. A perfectly horizontal movement to the right is called sensible heating. The temperature increases, but the moisture content stays exactly the same. A movement diagonally down and to the left is cooling and dehumidification. The air is getting colder, and water is actively being pulled out of it. But physical heating and cooling coils are not perfectly efficient. Some air will always slip through the machinery without touching the cold metal. Engineers call this the bypass factor. It means your pin stops short of its intended destination, because a fraction of untreated air sneaks past the coils and mixes back into the room. Calculating that exact visual gap on the chart ensures engineers never undersize the mechanical equipment needed to condition the building. The chart also allows engineers to split any complex diagonal journey into two distinct calculable parts. The horizontal component of that journey represents sensible heat. That is, the energy spent solely on changing the temperature. The vertical component represents latent heat. This is the energy spent entirely on pulling physical water out of the air. By comparing the lengths of these two lines, engineers know exactly how to split their electrical budget between cooling the room and drying it out. The psychrometric chart visually resolves a complex array of overlapping physics. It translates the invisible, shifting fluid dynamics of our atmosphere into a navigable geometric system. By mastering this map, we gain the ability to engineer our indoor environments and maintain physical comfort anywhere on Earth.